Good day. In our last class, we discussed the process of finding derivative of a function, okay, or derivative of functions, okay. So we have defined the derivative of a function for any variable x to be the limit as h tends to 0, f of x plus h minus f of x over h. Here we give an example of the derivative of a function x raised to the power of n, where this n is a positive integer. So we have been able to show that if f of x is x to the power of n, where n is a positive integer, then the slope f prime of x is given as nx raised to the power of n minus 1. So this is what we have been able to do in our first class. So and now we'll consider the second example given in the last video, which is f of x equal to ln x. Okay, so this is our second example in the last video, and let's quickly look at that using this derivative formula. So here, right, if you are given a function f of x equal to ln x, so in the formula we have the term f of x plus h. Okay, so we replace x plus h with x here. So this is ln of x plus h. So therefore, if we substitute this into the derivative formula, okay, so this will be the limit of f of x plus h, as we have it in the formula. This will be ln of x plus h minus ln x, okay, that is minus f of x, which is ln x. So this is over h, okay. So next is to evaluate what we have here. So this is equal to the limit as h tends to 0. Okay, so applying the law of logarithm, okay, I'm bringing what we have at the denominator here out. Okay, this is 1 over h, okay, into apply the law of logarithm to this. This will be a ln of x plus h over x. Okay, so this is what we have here. Okay, again, this can be rewritten as the limit as h tends to 0, 1 over h. Okay, so this is the ln of 1 plus, that is, or if you distribute this x on each of these, okay, so this will be h over x. Okay, so this is what we have. So we need to evaluate this further. So we are building this up now to evaluate it further. So this will be equal to the limit as h tends to 0. So we want to introduce a term here, okay, and then we reciprocate the term that we have here. So if you introduce the term 1 here, that's x over x. So here this will be 1 over x dot x over h. Okay, so if x cancels, so we retain 1 over h. Then this is the ln of 1 plus 1 over x over h. Okay, so you see that if we reciprocate this, that is bringing x up, this becomes 1 over x over h. Okay, so by law of logarithm, the term x over h can come to the power here. So this will be the limit as h tends to 0. So here we'll retain 1 over x ln. The term here is going to the power here by law of logarithm. Okay, so this will be 1 plus 1 over x over h raised to the power of x over h. Okay, so this term that we have here, okay, is what we refer to as a standard limit. Okay, the standard limit, let us state it here. Okay, if you have the limit of a function let's say the variable of a integration is now y, for example. Okay, so if you have the limit of a variable, let's say variable y is to the power of y. Okay, so as y here, if h tends to 0 here, okay, if this is y, if y is x over h, for example, here if h goes to 0, then y here goes to infinity. Okay, so we can change the variable underneath here to y tends to infinity. Okay, so this is a standard limit, and whenever we have this, okay, so by either by linear expansion or Taylor series, okay, so we can have this to be exponential raised to the power of 1. Okay, so this notion alone is exponential raised to the power of 1. Okay, so that is the assumption we will use to get what we have here. Okay, so we are removing this because we want to use this notion here. Okay, so this is equal to the limit we haven't applied the limit yet. Okay, so if this limit affects this term here, okay, so the whole of this term becomes, okay, this limit will not affect 1 over x, since 1 over x is independent of h, so we can bring 1 over x out. So this limit goes to this term directly. Okay, so this will be the limit as h goes to 0. Okay, so if you do a change of variable, so this is what it becomes. So since we already know what we want from here, so we'll just apply the limit to this directly. Okay, and this okay, so if you apply the limit to this directly, so this is equal to 1 by x ln exponential. Okay, so ln of an exponential is equal to 1, since this is an antilog of this natural logarithm. Okay, so since this is 1 multiplied by 1 by x is become 1 over x. So 1 over x is a slope of the function f of x equal to a natural logarithm of x. Okay, so that is that on the derivative of a natural logarithm. Okay, so we can now consider another example under derivative of function. So let us consider another function, exponential x. Okay, so let's call this example 3. Okay, so suppose we want to find the derivative of a function f of x equal to exponential x. Again, according to what we have in the formula, f of x plus h will be given as this. Okay, so now by substituting this into the formula, so when we substitute this into the formula, so this will be f prime of x will be equal to the limit as h tends to 0 f of, okay, so in the formula we need to replace this with exponential x plus h minus exponential x over h. Okay. Again, so if you apply the law of indices there to this exponential, so this will be exponential x dot exponential h. Okay, minus exponential x over h. Okay, so exponential x is common, so that can be factored out. So we have this exponential h minus 1 all over h. Okay, again, this limit is tending towards 0, so it will not affect exponential x since exponential x is independent of h. Okay, so accordingly, this will be exponential x, then the limit as h tends to 0, exponential h minus 1 over h. So this is what we have. Okay, so this limit notion is also a standard limit. Okay, this is also a standard limit. Okay, under the indeterministic forms of limits. And when we evaluate this, okay, the value of this is 1. Okay, so one can note it. Okay, so under the standard limit, this should be in our previous video, that when we have something like this where the limit is depending on the variable of the limit is h. Okay, so when we apply that, so we see that the limit of that is 1. Okay, and accordingly, f prime of x there is exponential x. Since the entire this is 1. Okay, so exponential x multiplied by 1, we have this. Okay, so what you are saying in essence is that if you are given a function f of x equal to exponential x, the slope of that function is also exponential x. So the slope of exponential x does not change, especially when we have the natural form as this. Okay, so let us also look at the derivative of a function of a rational function 1 over x. Okay, so let's call this example 4. Again, if you are given f of x equal to 1 over x, okay, we see that this is a rational function. Okay, so the corresponding f of x plus h is 1 over x plus h. Okay, again, so if we substitute this into the formula, okay, so we have this to be the limit as h tends to 0. Okay, accordingly, okay, this term will come minus this term. Okay, this is 1 over x plus h minus 1 over x, everything divided by h. Okay, so this becomes, again, we are bringing the denominator out so that this becomes this. Okay, so the numerator here, we look for the LCM, and the LCM of the denominator is this. Okay, so if you find the x plus h here will be x, so x times 1 is x, so minus x here will be x plus h, so times 1 is x plus h. Okay, so when we open the bracket here, okay, we find out that this will be the limit as h tends to 0, 1 over h. Okay, so when we open the bracket here, this will be x minus x. Okay, so that's 0, and open this, that will be negative h over x into x plus h. Okay, so since we have 1 over h here, so this h here takes care of this, so this cancels out, and then we are now left with this. Okay, so this will be the limit as h tends to 0, -1 over x into x plus h. Okay, so when we apply this limit here, the limit is what this limit is saying is that wherever we see h, we put 0. So accordingly, this will be -1 over x into x plus 0. Okay, x plus 0 is x, so x times x. Now the final answer would be -1 over x squared. So this -1 over x squared is the slope of the function 1 over x. Okay, so we have other few ones as well. So other example, let's look at other skeletal functions. Functions such as sine x, cos x. Okay, we can also find the derivative of such from functions too through the derivative formula. Okay, so for example, let's have a example. Let's move forward. This is noted, so we can rub it up. So example 5. If you are given a function f of x equal to sine x, okay, again, the corresponding f of x plus h is sine x plus h. Accordingly, so the slope f prime of x is given as this. So again, in the formula we have that sine of x plus h minus sine x will be divided by h. Okay, so under the trigonometry identity, this can be expanded to give sine x cos h plus sine h cos x. Okay, so the expansion of this is given as this under the trigonometry identity. Okay, so then minus sine x all over h. Okay, so here the term sine x is common here, so we can group this into 2. Okay, and then we can apply this limit on each of them. So since both all this term has one denominator, so this can be the limit as h tends to 0. Okay, so the first part will be grouping this with this. So sine x is common then, so we can say sine x into cos h minus, so when this term comes out, it will be 1 there. Okay, so what we are saying in essence here is that let us distribute this denominator on each of them. So we can give this a bigger bracket. Okay, so plus this, we have grouped this into a term like this. So we're going to separate this. Again, we have sine h over h cos x. Okay, so this is the second term to our denominator. So we are giving it a bigger bracket. So by law of limit, this limit will be applied on this, and it will be applied to this. So let's take this up. So this will be equal to the limit as h tends to 0 sine x cos h minus 1 over h plus the limit as h tends to 0 sine h over h cos x. Okay, so here again, here again, since sine x is independent of h, okay, so this limit will not affect this because this look like a parametric constant, okay, and from our previous video we have discussed that when we have a constant, okay, the limit does not affect it. So and because of that, this sine x can come out, so this limit will affect this time. This is called h over h plus, again, this limit will not affect cos x because this cos x is also an independent term. Okay. Okay, so this is cos x ln. So this limit will affect sin h over h. Okay, in our previous video, we have regarded this as a limit. Okay, when we evaluate this limit, okay, this gives us 0. When we evaluate this limit, this gives us 1. So these two examples are in our previous video. Okay, so the entire this is 0 when we evaluate it, and this is cos x. So the entire this time is 1. Okay, so accordingly, so this becomes 0. So this multiplied by this is cos x. Okay, so the derivative of sin x is cos x. Okay, so we can also consider a case where the function is given as a function f of x equal to cos x. Okay, okay, using the same process, we can obtain f prime of x to be negative sin x. Okay, okay, other trigonometric functions such as f of x equal to tan x can also be evaluated using the trigonometric formula. We also have a function such as f of x equal to sec s, that's the secant of a variable x. Also have cotangent form, which is cot x. Also have the cosecant form, which is cosec s. So all these trigonometric functions can be you can find their slope through this process as well. Okay, so this is where we end this video. Now, next class we'll discuss more examples under these derivative of functions. Thank you.